The objectives of the experiments are, first, for experiment 3, to determine the rate of reaction and the reaction rate constant for each run, and also to study the effect of temperature on the conversion in a continuous reactor at constant flow rate and residence time. And for ASPEN simulation, the objectives are to perform simulation by using ASPEN software, and then also to compare the result of simulation and experimental findings. And lastly, to discuss the result obtained based on theory. The procedure of the experiment are: first, 0.1 molar sodium hydroxides and 0.1 molar ethyl acetates are prepared. The feed solutions are filled into their respective tanks, and after that, the flow rates of the reactions are set into 0.26 liter per minute, and the temperature of the reactor is set to 50 degrees Celsius. Next, 3 sets of hydrochloric acids are prepared, and then after that, sample is taken and mixed with hydrochloric acids. After that, 3 samplings are prepared, and the mixture is titrated with sodium hydroxide to estimate the amount of unreacted hydrochloric acids. And the sampling is repeated at a time interval of 5 minutes. Next, the volume of 0.1 molar sodium hydroxides that used in titration is recorded, and 3 readings are taken. After 20 minutes, the experiment is repeated for the temperature of reactor at 60 degrees Celsius. Now I would like to tell you about the procedure of using ASPEN software. First, components of the experiment is set, which is ethyl acetate, sodium hydroxide, sodium acetate, and ethanol. And then after that, the methods of the simulations is choose. In this case, we choose Peng and Robinson's method, and the method filter is common. And then after that, the block diagram of the simulation is created. In this case, we choose plug flow reactor, and then 2 streams, which is the feed streams and the product streams. Next, the parameters of the reactions is set. The temperature of the reaction is 50 degrees Celsius, and then the pressure was set into 1 atm, and the compositions is set for 0.026 mol per minute for ethyl acetate and sodium hydroxide. And then after that, we can select the title for our simulations, and we also have to choose the input mode, which is steady state, and then the stream class, we choose conventional, and for valid phases we choose liquid only, because in these experiments the phases is only liquid. And then after that, the reactor types is choose, which is reactor with specified temperature, which is 50 degrees Celsius in this case. And then after that, the configuration of the reactor is set. The length of the reactor is set to 15 meters, and the diameter is 0.011 meter. For that, the volume of the reactor is about 1.5 liters. And then lastly, at the reactions, we created the reaction number 1. We input the coefficient and the exponent, and also the rate constant, which is 5.35, and the E 20.95 kJ per mole. And lastly, we select the reaction sets that we have created, and then check to select the reaction sets.
I'm Kai Wai. Now I'm going to present about the results. The table below shows the theoretical result, which is simulated by using ASPEN software at reactor temperature of 50 and 60 degrees Celsius, where the inlet and outlet mole flow of reactants and products have been shown. The theoretical results have been tabulated in the table below, with the theoretical residence times is calculated by dividing volume with volumetric flow rate. The experimental result is being tabulated at the table above, with the experimental residence time taken when the conductivity is constant for over 3 values, whereas the error percentage is tabulated in the table below. This graph is showing how temperature affects theoretical conversion and theoretical rate of reaction. They are both increasing with increasing temperature. Whereas this graph is showing when temperature increases, the theoretical rate constant will also increase. And this graph is showing how temperature affects the experimental conversion, experimental rate constant, and experimental rate of reaction. When temperature increases, both experimental conversion and experimental rate constant is decreasing, whereas the experimental rate of reaction is increasing with temperature. When temperature increases, the experimental conversion decreases, whereas the theoretical conversion is increasing. This is because it's an exothermic reaction, and it obeys the collision theory. When the particles are being heated up, they move faster and collide more frequently, and the energy processed by the molecule is high enough to overcome the activation energy. Lastly, the effective collision occurs, and thus the conversion is increasing with temperature. Next, this graph is showing when temperature increases, the experimental rate constant decreasing, which is derived from the theoretical rate constant, which is increasing with temperature. Referring to the Arrhenius equation, when the temperature increases, the exponential term increases, thus the reaction rate constant will increase as well. This graph is showing when temperature increases, both experimental and theoretical rate of reaction will increase, and they all obey the collision theory, where the particle is being heated up, they move faster and collide more frequently, and thus rate of reaction will increasing with temperature. This graph is showing when temperature increases, both residence time is constant. It's because the reactor volume is constant at 1.5 liter and the flow rate is constant at 0.52 liters.
I'm Kaikin. I will explain about the sample calculations part. First of all, the reaction in this experiment 3 measure chemical reaction rate in plug flow reactor PFR is ethyl acetate mixed with sodium hydroxide to produce sodium acetate and ethyl alcohol. Step 1. We calculate the concentration of unreacted NaOH. By using the data at time t equal to 10 minutes and temperature t equal to 50 degrees Celsius, concentration of unreacted NaOH is most of unreacted NaOH in the sample divided by volume of the sample times 1000 mol per liter, and we get 0.029 mol per liter. Step 2. We calculate conversion X. Conversion X is the ratio of feed consumed or the ratio of the product form. In this experiment, conversion is concentration of NaOH that has reacted divided by initial concentration of NaOH. So the concentration of NaOH reacted is the initial concentration minus the concentration that has reacted. and we get 0.7070. Step 3, we calculate reaction rate constant K. Reaction rate constant in chemical kinetics quantifies the rate of a chemical reaction and it depends on temperature. Its formula is 1 over tau Ca naught times x over 1 minus x. By plug in Ca naught, x, and tau, we will get final value of K is 5.440 liter per mole per minute. And we come with the final step, step 4, which is calculation of rate of reaction. Since it is a second order reaction, we use the formula negative Ra equal to K Ca naught squared 1 minus x squared. By plugging in the value of K, Ca naught and x, we will get negative Ra equal to 4.58 times 10 to the power of negative 3 mole per liter per minute. Conclusion part. At 50 degrees Celsius, theoretical conversion is 0.9980, while the experimental conversion is 0.7070. The error we get is 29.16%. At 60 degrees Celsius, theoretical conversion is 0.9983, but the experimental conversion is 0.6680, with an error of 33.08%. Overall, the theoretical results simulated by ASPEN has large deviations compared to experimental results. The error might caused by the problems that occur in the experiment, which is the flow rate of the feed solution is not monitored constantly with regular checks. Hence, there is deviation in the concentration of NaOH samples collected. So what should we do? To improve the accuracy of the result, there is some recommendation. First, 5 ml of HCl should be added into the sample taken immediately to stop the saponification reaction. Secondly, parallax errors must be avoided when taking the reading of the volume of NaOH used in the burette during the titration and measurement of solution volume. Third, titration should be carried out carefully in order to make sure that the pH of the analyte is exactly 7. Fourth, the flow rates of the ethyl acetate and sodium hydroxide should be adjusted constantly to make sure that they are in the range of plus minus 10%, because a large deviation in the flow rate will affect the accuracy of the result. Lastly, the conductivity should be taken after it shows 3 constant readings before the sample is taken out from the detector. So that's all from me.